Welcome to Chino High Math Help. This is going to be our first episode, and we had a topic requested by, I think it was at Mr. AP42, also known as Eric Chavez. And so today we're going to be covering three topics: the Bernoulli Trials, binomial probability distributions, and geometric probability distributions. And these three topics are applicable to the class we have here, AP Statistics. So first off, I want to cover Bernoulli Trials. Basically, what a Bernoulli trial is, it requires three conditions. So one is that there's only two options, and that is our success and our failure. And I'll get to that P and Q later. Two options, success and failure. The second is that we have a constant P, which P I'll refer to the P as our probability of success, which I'll go into detail later. And then also three is that the trials are independent. This means that each trial occurring consecutively does not affect the outcome of the next one. So I want to get into this P and Q thing here. So P, I'm going to think of some number, I'm going to go with 0.7, and Q, I'm going to make that equal to 0.3. Here's why. So P, as I said earlier, is our probability of success. So this 0.7 really represents 70%. This Q we refer to as our probability of failure. So in this case, 30%. And if you haven't noticed, P plus Q, that could be rewritten as 0.7 plus 0.3 should be equal to 1. If you're currently in AP Statistics, you should be familiar with the fact that if you add up the probability of all possible outcomes, in this case, the two outcomes, you should always get 1. Next, I want to give an example of a Bernoulli trial to kind of clarify what I mean by all this. So let's picture you're at a sporting event, let's say a water polo game, and there's a really good goalie, and you're taking penalty shots. So probability of success, and in this case the success would be you making the goal. Let's say you have a 80% chance, so 0.8. Probability of failure, meaning you either miss or the goalie blocks the shot, would be 0.2. And we know this because Q must be equal to 1 minus P. So 1 minus 0.8 equals 0.2, as we saw here, because P plus Q must equal 1. Two things you might be able to do with this situation are looking for an exact number of successes. So we might say probability X equals, let's say, 4 successes. And I'm going to say that N equals 5 for this. What I mean by that is we have 5 trials. As we call these Bernoulli trials, each trial has 2 options, and each time we run through it, it's just a trial. And so that's N equals 5 here, and what I mean by this is P of X equals 4, X being our number of successes. So for here, P of X equals 4, I am saying that this is the probability that we have 4 successes within our 5 trials. Another thing you might want to look for, or another thing that you might have to look for here, is that the probability that you get at least 2 successes, or the probability that you get less than 3 successes. There's a lot of different situations like this, which is where we get into binomial and geometric distributions. The first examples I want to talk about are actually geometric. So geometric probability distributions are usually useful for looking for a number of trials, meaning our N, until we have a success, which would be our P. And so for our geometric, the only really thing we care about here is our P, which, as we referred to before, was the probability of success. Let's say, for example, in the last one we had a probability of success was 0.8, and our Q, probability of failure, is 0.2. In geometric model, we're looking for a number of trials until we have a success. So let's say we're looking for a number of trials. I'm going to make a variable X. Probability that X equals 5. It's 5 trials until a success. If you have 5 trials until a success, that means you're going to have 4 failures, which would be 0.2 and raised to the 4th, because that happens 4 times, and then a success, 8. This is the standard formatting we see for looking for successes and failures. Now is the probability of this. And that's our probability here of having our first success on the 5th trial with a probability of 0.8. Probability of success of 80% or 0.8. So this was an example of looking for the probability of having 5 trials until we have 1 success. So the way we want to write this out usually is the probability, I'm going to use a big X here, for just our variable there, equals and n, so some number of trials, and this represents the number of trials until our first success, is going to be equal to our probability of failure, get rid of that parenthesis there, raised to n minus 1. So here our n was 5, and I raised that to 4, because we had 4 trials with failure, and our final trial here is p, a probability of success. And that'll give you the probability that your first success is on your nth trial. Two more important things with geometric distributions. This is the probability here, but our expected value, here we see e of x, so expected value of x, or variable x, is equal to mu, which we can see as a mean, or also expected value here, is equal to 1 over p. What this means is that it's our expected number of trials. As we saw, x was our number of trials until we reach success. So with p equals 0.8 here, we're going to have e of x equals mu equals 1 over 0.8. And so 1 over 0.8 gives me 1.25. What this means is that on average, or what we expect to see, is 1.25 trials until we reach success. Statistically, logically, this doesn't really make sense because you can't have 1.25 trials, but statistically it does make sense. And so that's our mean, but one thing that always comes with the mean is the standard deviation. And here we see that denoted by this sigma here. And so the standard deviation is equal to the square root of the probability of failure over the probability of success squared. So in this case, we have sigma is equal to the square root of 0.2 over 0.8 squared. Yeah. So with this sigma is equal to the square root of the probability of failure over the probability of success squared. And so here, what I got from this is 0.5590 for decimal accuracy. If you're in stats, you should be aware that that's always the level we go to. And what we see from this is our expected value is 1.25 trials. So we expect to have 1.25 trials until we reach success. But we can also expect a standard deviation of 0.5590 trials, meaning that it's not going to be very uncommon for this number to be about 0.5 trials off. So if I was to take half a trial off this or add it, you could say it's going to be within maybe 1 or 2 trials until we reach success, which makes sense. With such a high probability of success, probably aren't going to need that many trials. So previously we covered geometric probability distributions, and now we're going to move on to binomial. So geometric, all we really cared about was this p being the probability of success. And with geometric, what we're able to calculate is the number of trials necessary until we reach success. And with binomial, what we're going to be doing is seeing the probability of getting a certain number of successes. Here we're going to be representing that with k in a certain number of trials, represented by n. So I know this looks big and complicated right now, but we can leave that. We are familiar with the geometric form of seeing what's the probability of getting your first success on your first trial. And I'm going to use the values we had earlier, p equals 0.8 and q equals 0.2 for this example. So the probability that you get your first success on your first trial, well, that's just going to be 0.8. 1 trial and you're successful. The probability that you have your first success on your second trial, you're going to have 0.2, which is a failure, multiplied by a success. And as if you are currently in AP statistics, you are aware that this is kind of a and situation. And so when we have the probability of A and B, this is going to be equal to the probability of A times the probability of B. In this case, we have a failure and a success. And if we wanted to see the probability of getting our first success on our third trial, we would do a failure, and we're going to square that now. That's 2 failures and a success on our third trial. Probability of getting our first success on our third trial. with binomials, we're looking for a certain number of successes within a certain number of trials. In this notation here, our n and k, our n represents our number of trials, let's say 5 trials, and our k represents our number of successes, and let's say our goal here is 3. So in this notation, we're going to be looking for the probability of having 3 successes within these 5 trials. This can mean that you have a failure, failure, success, 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 or failure, success, failure, success, success, maybe. This is disregarding the order. This is simply the probability of having any 3 successes within 5 trials. For this, in our binomial probability models, we're going to be using n, c, k here. This is the notation here, and this is referred to as n choose k. So I'm going to rewrite this with the variables that we've chosen here. I'm going to have 5, c, which is choose, and k, which is my 3. So 5, choose 3. We refer to this as a combination, and we use this in our binomial probabilities to once again see the probability of having 3 successes within 5. Knowing only the geometric approach to finding probabilities of numbers of successes, you might be tempted to, let me rewrite my numbers here, 3 successes within 5 trials. You might be tempted to just say, well, the probability of having 3 successes, well, that's obviously going to be the probability of success cubed times the probability of failure squared. There's 5 trials. This makes sense, but it's flawed. You're missing something. And this is our combination here. Our combination is where it gets a little bit complicated. I'm just going to think of some number here. I'm going to use 4. Exclamation point there. We call this a factorial. This is said as 4 factorial, and all that means is 4 times 3 times 2 times 1. And I mean, if you want, you can disregard that 1 because it's not going to do much for us. But 4 times 3 is 12 times 2, you get 24. So we say 4 factorial is equal to 24. In this case, we have that our n ck, so n choose k is equal to n factorial over k factorial, and then multiplied by the difference between n and k factorial. So for here, our n is 5, so 5 factorial, and I forgot to write this real quick. So we have 5 choose 3 equals 5 factorial over our k here is 3 factorial, multiplied by n is 5 minus k, which is 3 factorial. Might look a little complicated, but here's where it gets pretty easy. 5 factorial is really 5 times 4 times 3 times 2. I want to leave out the 1. Over 3 factorial, 3 times 2. Times 5 minus 3, which hopefully we all know that's 2. 2 factorial is just 2 times 1, or just 2. Now you can see I can take this 2 here, cancel that 2, cancel that 3. 5 times 4 is 20. Over 2 is 10. So in this case, we are looking for the probability of having 3 successes within 5 trials. As we said the geometric before, we attempted to go p cubed and the probability of failure squared. 5 trials. And now we're going to need to multiply this by what we just calculated in the last step, which was our 5 choose 3, which we saw was equal to 10. We multiply 10 by this probability, we will get our probability that x equals 3. In this case, I'm saying 3 successes. That's what my x is representing here. And now if I crunch the numbers, 0.2048. This means is we have a 20.48% chance of having 3 successes within our 5 trials. And that's what we use binomial probability distributions for. One final thing for binomial models. We saw in geometric that we were able to calculate the expected value of x, also written as mu. And in binomial, we are concerned with the number of trials. So our expected value of successes within a certain number of trials would be our p, which is our probability of success, multiplied by our number of trials, so NP. And we also calculate our standard deviation, written as sigma, and this would be the average deviation from this number given a certain number of trials. And we calculate a standard deviation with the square root of NPQ, which is our number of trials multiplied by our probability of success multiplied by our probability of failure. I just want to finish this video off with a little summary. So Bernoulli trials, we saw that there's 3 conditions for them. You have 2 outcomes. 2 outcomes are success, represented by P, and failure, represented by Q. They're also constant P, meaning that the probability of success remains the same throughout, such as P equals 0.8. That means there's an 80% chance of success, and that should remain constant throughout each trial. And finally, the trials must be independent, meaning that the outcome of one trial should not affect the outcome of the next. We'll use binomial probability distributions to calculate the probability of having a certain number of successes within a certain number of trials. And this is represented by a certain number of successes. Could be k equals 3, and our trials could be 5. And from there, we're going to use n. We're going to use n, choose k, times the probability of success by raised to the number of successes. Let's say k in this case, multiplied by the probability of failure with n minus k, which we covered earlier in the video. For geometric distributions, you can use those to look for the expected number of trials until we have a success. And we can also see the probability of having a certain number of trials until we reach success. So for geometric, we might see the probability of x equals 4, meaning 4 trials until we have success. The probability that x is going to equal 4 trials, well, we're going to have 3 failures, so 0.2 cubed times the probability of success, 0.8. And also important in geometric distributions, also important in geometric distributions, we have the expected value, meaning the expected number of trials, which we can also write as mu, is equal to 1 over p. And the standard deviation of the number of trials until we reach success is equal to the square root of q over p squared. Or we can write that as the square root of q over p.
Alright guys, my name is Uri Chavez and I approve this message.